Okay. I have it on already now.
You have it on?
Yeah.
I think he said it's good.
Okay, and then would you mind doing a quick sound check?
Is it me?
Hello? Hello? Good. Okay.
Okay, yeah.
Just want to make sure that we're good here.
Okay.
Good.
Thank you.
Yeah, thank you.
Thank you, and we're ready to go live when you are.
Okay. Thanks.
Absolutely.
Thank you, Chris. 你看，它就是 Zoom 上的人可以看到，可以是这个屏幕，
整个的
然后
I see
他有人做呢，专门给你一会儿弄一下，一会儿弄一下，然后
I see
Zoom 上的人可以专门看屏幕的，
嗯哼
然后也可以专门看你的，
OK
就这个还比较 fancy。
I see.
所以昨天买那个东西是可以的，那个 solution。
可以，多谢你，多谢你，要不然我今天得瞎着眼睛来。这个钟都不一样。
我这上面是58。
嗯，所以这个是准是吧
58。
？OK
那很快就听懂了。
OK。你们一般也是5分钟之后开始吗？还是准时开始？等2、3分钟。
Okay, I think we can get started. Good afternoon, everyone. Welcome to today's BMI seminar. I'm so happy to welcome Dr. Yan Ma to Vista Medicine in person. This probably is the first external speaker after the pandemic for BMI seminar series. And before her presentation, I will briefly introduce her. She is currently a professor of statistics at Penn State University, and he has huge expert in semi-parametric statistics and a lot of applications. Well, actually, I should say she's a master of using, more than expert of using semi-parametric statistics. She's not only a theoretical statistician, she also considered a lot of problems in biostatistics, such as causal inference, missing data, measurement error, case control studies, and also a lot of latent variable-based models. She made influential and fundamental contributions in dimension reduction, measurement errors, and so on and so forth. If you check her publication list, I'm pretty sure you will be amazed by her publication record. She is a fellow of ASA, American Statistical Association, fellow of IMS, Institute of Mathematical Statistics, and also an elected member of ISI, International Statistical Institute. And actually, personally, I'm so grateful to know her in the past many years. I'm so fortunate to collaborate with her on lots of projects. I learned a lot from her, not just the semi-parametric statistics, but also her attitude of doing research and how to be a better researcher. And today, she is going to talk about the network functional varying coefficient model. And without further ado, the floor is yours, Yan.
Thank you, Julie, and for the very generous, flattering introduction. I'm not sure I deserve that. So I'm glad to be here. This is my first visit to Wisconsin, and the weather is quite similar to Pennsylvania, actually. We are also at the same kind of temperature. The talk that I'm going to give today is network functional varying coefficient model. This is a joint work with two collaborators. Xuning Zhu is the real expert in this network data area, so I actually learned all these things from her. She once was visiting Penn State for a whole year. I got to know her then. But funny thing is, during the whole year, we didn't talk about research at all. And then later on, when she went back to Fudan University, I went to Shanghai to visit her. And then this is the opportunity for us to get started on this project. And with the situation now, I don't know when I'm going to visit Shanghai again. And Zhan Rui Cai at that time was a student in our department, and he is the one who implemented all these methods numerically. And now he's going to join Iowa State University as a tenure track faculty very soon. Okay, so here is an outline of the talk. I will first introduce the model and explain some background on that. And then in terms of the methodology, we have two components. One is in the functional coefficient estimation and also the inference, and the other is about the functional principal component analysis. And the numerical part will cover two parts. One is the simulation work, and the simulation work, depending on the time, I might need to skip it. And then it's also a real data analysis. That's the social network data. This is a social network in China, because that's the data we can get. And then I will wrap up with some possible extension and potential future works in this area. Okay, so before I talk about network functional varying coefficient model, I want to first talk about the more classical version. So the more classical version is the functional varying coefficient model. And that model has been studied quite extensively, and I listed all these literatures. So the model itself is written down here. YIT is the response. It's a functional data, so YIT is a function. And then it is linked to the covariates linearly through this Xi transpose beta T. And then there's the innovation part, that's the eta IT, and then there's the noise part, epsilon IT. So just for convenience, usually people just assume t is between 0 and 1. So that's the typical varying coefficient model. Varying coefficient because of this beta t. So if your beta is just a constant parameter beta, then it's just a linear model. And then this eta IT and epsilon IT is the pure noise part. It's assumed to be white noise with variance sigma squared. And eta IT is capturing the time evolution. So this is, there's a dependence at different time t. So that's the eta IT part. So like I said, the varying coefficient model the functional varying coefficient model has been studied quite extensively. So the only thing we did is add a little bit change to it. We added this component here, rho t times mi inverse times the sigma of aij yjt. And this is because sometimes you might think that maybe those functions at different I, they are not really IID. They are influenced by each other. So if YIT is influenced by YJT, the simplest thing you can do is to do a linear model. So that's YIJ times YJT. And of course, this YI can be influenced by all different YJs. So we have a summation form here. So here, this AIJ, it depends how you want to model the network. Maybe Yi and Yj, they are friends of each other, it's 1. And if they are not friends of each other, it's 0. So it could be just 0, 1 binary variable, binary number. Or it can be something between 0, 1, let's say. It not only qualitatively you are friends or not, you can also have how strong your friendship is. So how big is the influence? So that's Aij. So either case, it should work in our case. And then this Mi is just a normalization. So we want this Aij to sum up across J with a fixed I. We want it to sum up to 1. So that's why we divide by the sum of those Aijs. That's the Mi inverse. And then finally, we have this coefficient rho of t in front of that. And that is describing the strength, the network connection strength. So if you are friends with each other, how large is the effect that I will be affected by friends? So that's the only additional component we add. And this is called what we call a network functional varying coefficient model. So all other aspects are the same. And this rho t, in fact, in the analysis, we need to restrict this rho t to be between absolute value to be smaller than 1. So it's describing the network connection strength. So the observations, it's written as xi for the ith person, and it is yi. And of course, you do not observe the whole function. So you observe at a bunch of points. We assume it's observed at ti1, ti2, up to ti and I. And of course, these points doesn't have to be the same for different individuals. And the total number of I goes from 1 to capital N. So you can imagine this I is the number of individuals. And those YITs are the behavior of different individuals. And the network is, the AIJ is a network description, describing if the two persons are connected or not connected. Okay, so that's our description of the model. And it's quite unfortunate that I need to introduce a bunch of notations before I go on. So let me go through those notations now, and if you can,
Sorry, and there's a question. How do you incorporate prior time point influence in the model? That is from 1 t minus 1.
Oh, we don't. Yeah. So this is a simple case. We only assume my behavior at current time is affected by other people's behavior at current time. So yeah, the question is more advanced. You want to have the other people's previous behavior affect my current behavior. I will mention a little bit about that at the last slide, actually. It's a lot more complex if you want to incorporate that. Yeah, that's a very interesting question. Yeah. Okay. All right, so in terms of the notation, if I put all those YITs together, you get vector functions, and that's the bold-face YT. And if you put all those X covariates Xi's together, you get a matrix, and that's our boldface X without any index. And that Aij, once it's row normalized, we give it a name, and that's the W. So that's the W matrix. W is a known matrix, so we know if two people are friends or not, or how strong their friendship is. So the innovation term eta IT and put all together, and we get this this curly eta T. And the white noise, we also put them together, and that's the curly epsilon T. And then this is the one matrix that comes up all the time in our analysis, so we give it a name as well. That's the identity minus this rho T times W, and that's what we call S of T. So maybe that's the only notation that is not very intuitive. And then all those functional parameters, rho T and beta T put together, we just give it a name theta of T. Okay, so like I said, these names are all quite intuitive, and the only thing that you may have to make an effort to remember is this S of T. Okay, so once you have those notations, then the previous model, we can put everything together into the matrix form, and that's the matrix form. So this is YT equals to X times beta T times rho T W times YT, and then plus this innovation eta T and epsilon T. So of course, you can just move the Y to one side. But that's how this ST comes up. If you move rho T times the W to the left-hand side, you have an ST times YT times whatever is remaining on the right-hand side. And then you can, of course, multiply this ST inverse on both sides. And this is what we get. So once you get this form, then it looks very much like a classical model that you can handle. And we will later see why this is not such a bright idea. Okay, so because we also need to do functional principal component analysis, so let me just introduce a little bit more notations. And these notations are standard notations. So for, at least for people that does functional data analysis, this is just routine. So we assume this eta IT, you can do the expansion as the beta ik times the basis function theta k, phi k of t. And then those BIKs are uncorrelated with the variance, lambda k, the eigenvalues. And the eigenfunctions are those phi k. And of course, they are orthogonal. And the covariance variance function is written as C of SMT. Okay, so that's our notation. And the functional principal component part is the second part. So if you forget at that time when we need it, you can ask me again.
So there's a question.
Yeah.
Whether ST is always invertible.
Yeah. So our rho has a requirement. This rho has to have absolute value smaller than 1. Then it is invertible because W is also normalized. Okay. So now I just copied that YT equals to this S inverse something, this whole expression from the previous page here. And we remember that in our original setting, this YT is not observed at fixed points for everybody. But we step back a little bit, we do a simplified case. So let's first assume YIT is observed at the same time for all the different individuals. So if this had been the case, then life is a little bit easier. We can use basically MLE to do the estimation. So let me first, it's another notation, this sigma epsilon star squared is the variance of the two components together, eta and epsilon together. And that variance, you can decompose it into the variance covariance of this eta and the variance covariance of this epsilon. And that's the CTT plus epsilon squared t, according to the notation we introduced before. Okay, so for now, we at the original problem, we didn't assume epsilon to be normal. But we also didn't assume this eta to be normal. But if you pretend they are normal, then you can use MLE to do the estimation. And this is what we get if we perform just the straightforward MLE. and that's the form. And because the original model didn't assume it is normal, but you assumed it's normal to derive the MLE, so that's why people call it quasi-MLE estimator. So it turns out that this is valid, and it's also quite efficient because, of course, it's MLE, and the computation is stable. And even if your original data is not a normal, you pretend it's normal, you perform the MLE, it does not really hurt you much. So that's what we mean by it's often efficient and stable. And the drawback, so if you take a close look at this, the target function you want to maximize, the log of the MLE, the log of the likelihood, you see that there's this log of ST. This absolute value means the determinant. So you actually need to compute the determinant of ST. So ST has the size n times n. So if your sample size, the number of people, the network size, becomes very large, so this is a very large matrix, and you need to compute its determinant. So that's a very, computationally, it's a very big challenge. So that's the main drawback of this quasi-MLE estimator. So what we actually end up doing is, in fact, a kind of composite likelihood. Composite, not really likelihood, composite LSE, least square estimator. So again, the transformed model is written as on the first line here. And we still pretend we have the normality for both eta and epsilon. So in that case, you can write down so-called so the original least square, you would have YIT subtract its mean. And here what we do is we use YIT but subtract its conditional mean, taken this observation, the YI out, conditional on everybody else. So you can see if it had been an MLE, and if you replace the expectation using conditional expression like this, this is a kind of composite likelihood. So now we started with a least square form, and we also do this kind of replacement. So that's why we call it composite LSE. So now once you plug in that form and you carry out the computation, what you end up with is this expression here. And the inverse times the L2 norm of this whole bunch inside. So in this whole bunch, you have, first of all, you don't need to invert your ST anymore. And what you have is to invert this so-called, the D of T is the result of an inverse. And that's the only place you need to do the inverse. And that inverse is inverting a diagonal matrix, the diagonal matrix of this M of T. And that M has this expression, identity plus rho squared W transpose W. So this, by the nature of it, it is a lot simpler to compute. You don't have to compute a large matrix inverse, or you don't have to compute the large matrix determinant. And even though we derived it under the normality, the final form is actually, you can show it is consistent even if you do not have the normality for epsilon and eta. So this is a byproduct, and we actually do not quite understand why. The first expression, so this should be valid, that's for sure. But the computation, the detailed computation actually use the multivariate normal property. And in the end, the result we get does not depend on the multivariate normality. So that's quite a surprise for us as well. Okay, so yeah, so that's the form we end up using. Remember that this is a form we end up using under the hypothetical situation, that you have data lined up for different individuals, you have the same time for the observations. So we need still to handle the non-homogeneous observation time. But before I go on that, I want to point out some other features of this function, the target function we try to minimize. So again, I copy that function down, and then on the second equality, I just expand that matrix out to see what is the detail. So what you see that the WJIs, those are the normalized AJIs. So these, you see the square of that and you see by itself. And this, or the two W's multiplied together. So these are the only, you don't have, for example, you don't have 3 W's multiplied together. So this is saying that if you have, so if a single Wij is non-zero, that means I and j are connected. If Wij times, so here I use Wj prime I and Wj prime j. If that one is non-zero, that means I have 2 people are connected through one common person in between. So that means only those people that are directly linked or people that are second order friends will be non-vanishing here. So all other further friends, they will disappear. They will not participate in this calculation. So this is saying that you actually have a lot of simplification. If your friends, if your network is not very dense, you have a few links here and there, then this computation is is very simple because only the first and second friends are involved. Okay, so this is not our new proposal. Similar idea has been used in this Huang et al. 2019 paper, and Zhu is the same, Xuening Zhu, her paper. Okay, so now let's handle the situation that you do not have the same observation time for different individuals. So we have YIT observed at TI1, TI2 to TI and I. So to handle that, it's just to make the writing shorter. So I gave it a name. So this guy here, D times S transpose S times EI, we call it UI, and this D S transpose X beta, we call it this is a Xi, right? Xi of theta T. And then we can write out this Q into this form. Of course, the detailed calculation, it takes some time, but just believe me that this is the right way of writing it. And this YIT is supposedly the observed ith function. YJT is the observed jth function. So now, if I imagine, well, this is not really just imagine. This is the truth. My YIT was something plus that noise part, right? If that's something, I call it Y star of T. And then YIT is, if you could have Y star of T, you are even better than using YT, right? If you have, YIT is a noised version of Y star T. So if in these, in that calculation of the Q function, if I replace all those YI, YJs with YI stars, I'm better off because now I can use the denoised data. And so that's quite important. So your QT, your Q function is the function you need to optimize. And if you could improve that target function you try to minimize. And the improved version is this one here. So I just replaced all those Y's with Y stars. So now, of course, you cannot have those YI stars. You do not even have the YIs. But the reason we replace YI with YI star is that now you can actually estimate those YI stars. Estimating YI is impossible, but estimating YI star is possible. And here is how we are going to use the non-parametric kernel approach to estimate those two quantities. One is the YI star times YJ star. The other is the YI star. So let's take a look at the YI star. YI star is easier. It's just the classic, where do I write it? Yeah, here. YI star is the standard kernel approximation. So we use YI star using this so-called eta HIT divided by f hat HT. So this f hat HT is the density of T, and we just use the kernel approximation, and we collect all the observations. We use not only the ith person, but also other people's observations to approximate this f of t. And then on the denominator, we use only this ith person's observation to approximate that. So that ratio gives us this is the classic regression for yi star t. So to estimate yi star t times yj star t, it is a little bit tricky. So when I is not j, this is the standard approximation. You just use the yit, whatever you observe, yjt, whatever you observe, the pairs, and you use the double product kernel to approximate it. But when I equals to j, you need to extract the situation where you have these two times the same. Because if they are the same, then the observed yi has the additional error, and that error will give you an epsilon square, and that will generate a sigma square, and that's not what you want to estimate. So in this case, we only take those pairs when these observed t's are not the same. Okay, so that's how we can approximate this yi star times yj star and the single yi star using the kernel approximation. So now, regardless of what t you want, I can always approximate it. So that solves the issue of non-homogeneous observation. And then once we replace those stars with the estimated version, the target function is named q tilde, and then we just minimize that q tilde to get our theta. Okay, did I make it clear, the procedure? So that's it. That's the estimation. That's the whole estimation procedure. Basically, it's a combination of composite least square and the non-parametric kernel regression. And then afterwards, I need to present some theoretical results of this procedure. And let me give the conditions, the condition sets first. So we have quite a lot of conditions, and the bottom line is that those conditions are quite standard. So they are all conditions required in the existing literature. Because we involve network data, we involve functional data analysis, we also involve non-parametric kernel methods. So all these different branches have their own regularity conditions. And our results are all classic in either of those literatures. So first of all, this C1. C1 is about the distribution of those observations. And you can see that we have some moments condition, and these are all standard. And then for the function, we also have sufficient smoothness. We also require sufficient smoothness and some bounds on some functions. So these are also quite standard. So I'm going to not get into detail. And the whole set of C3, this is the standard requirement in the network structure. So in network data analysis, they typically view this W as non-stochastic, and we also view it as non-stochastic. Actually, it's just a fixed matrix given there. And then there's some requirements on the connectivity of your W, and some regularization of your W, some homogeneity of your W. And this is written as the regularization is reflected through the binding the maximum eigenvalue of this W plus W transpose matrix. Okay, so this is that requirement. And here I want to mention, I want to mention this condition. This E transpose W to the K times 1 is the vector of all ones. So W to the K is the kth order friends. And once you multiply a 1, hence EJ, that is describing this is EI. This is describing for the ith person how many kth order friends this person has. So now we have a restriction on that. This cannot grow too big. It is of the order log n to this KW. So this is sort of restricting the superstar effect of the network. So we cannot allow one person that has a lot of followers. So that's called a superstar effect. So this kind of effect will destroy the homogeneity of the matrix of the network structure. So that it's not totally forbidden, but it's restricted. There's a certain order that we require. Okay, so that's the C3 sets, and then C4. This is a covariate requirements on the covariate. Basically, this is requiring the second moment of the covariates to certain second moment type of relation to exist. And then C5, C6 is the conditions from kernel regression. So this is about the bandwidth and about the kernel function that we use. So here, I want to mention one more thing is that the bandwidth H. So the bandwidth H is linked to this minimum number of observations per individual. So for the individual I, the number of observations is Ni, and N minimum is the minimum of the individual number of observations among all individuals. So the bandwidth H square is of smaller order of this N minus 1/2 minus delta 1. Delta 1 is some kind of constant. And it also has to satisfy the minimum number of observation times H is larger than this N to the order delta 2. Delta 1, delta 2 are both positive constants. So you can see when my capital N is the number of individuals. When my capital N is bigger, my requirement on H is smaller, right? I need a smaller H. And when I have a smaller H, my N minimum needs to be larger, right? This is smaller. On the left-hand side, H is smaller. On the right-hand side, N is bigger. So N minimum has to be larger. So this is saying that when N goes to infinity, my number of observations per individual is very dense. And this is indeed, in the functional data, this is called the ultra-dense observation. And so this is the context that we work in. Okay, so yeah, and then the final requirement, C7, this is about collinearity type of thing. So that your covariate covariate matrix, your covariate has to be sufficiently has non-collinearity. Okay, so here are the results. So first of all, this is a pointwise result. So under our condition C1 to C7, that condition that I just listed, we have the convergence, the consistency result. So theta hat minus theta t is of the order n minus 1/2. And we also have the asymptotic normality. So this is the writing of the asymptotic normality. So I want to mention, so this is a pointwise result. And the convergence rate we get here is n minus 1/2. So if you think about the data we have capital N individuals or nodes, if you want. And then for each individual, we have at least n minimum observations. So the total number of observations is n times n minimum. And then since we are using the kernel method, so we should have n times n minimum times h minus 1/2, this kind of rate. So, but we don't. We only have n to the minus 1/2 rate. And the reason is because we have the time correlation. So the functional data, each observation is time correlated, so they are not independent. So that's caused by the time correlation.
And there's a question.
Yeah.
Could you go back to condition C7?
Yeah.
Is tau in C7 random or
Tau is a constant. Yeah, so tau, delta 1, delta 2, these are all constant. We require that they are fixed constant so that this thing is larger than tau. Okay. Yeah. Okay. Yeah. So I just explained that we don't have the classic n times n minimum h minus 1/2 rate because we have time dependency, within curve time dependency. And this rate we obtain also is consistent in consistent to the existing literature. So in the functional data literature, without network linkage, people have obtained the same kind of rate as us. Okay, so so the next thing I'm going to talk about estimating the variance covariance function. So this is part of the second part of the estimation. This is the functional principal component analysis. So standard approach for this type, for if you don't have the data feature we have, the standard approach in functional data analysis is first to estimate this eta IT individually using this expression here. And then you form your variance covariance matrix C hat, a variance covariance function C hat of ST using this expression here. So that's the standard approach. And of course, for us, this is not feasible. This is not feasible because we do not have the Yj at Tik. We only have Yj at Tjk, but at all other Tiks, we do not have it. So, so what we propose to do is we do it in this way. So we directly estimate this C, the variance covariance function CST first, and then from there we estimate eta IT using the eigenvalue decomposition. Okay, so first of all, we figure out if you take S times Y minus X beta, so that leaves you only the eta plus epsilon part. And you take its variance covariance matrix, variance covariance function. What you get is the function you want plus this contribution from the pure noise, sigma epsilon squared. So this is just a fact. So now what we are going to do is using this relation, we're going to get our analysis estimate for CS and T. So here we write out we extract out the we extract the diagonal term. So that's diagonal, you have n of them. So you have n times CST times this thing equals to, if you calculate that variance covariance out, this is the expression we have. So once you have that expression, the method we do is very similar to what we did in the previous kernel approximation. So we are going to use kernel method to estimate this expectation of Yjs times Ykt. That's the only thing we need to estimate. And here is the expression. So again, one thing that I need to point out, I don't know why this is red, but this is not showing the color. Okay, do you see it on your screen?
If the screen shows this whole screen, it shows, but if it shows the whole screen, it does not.
Okay. So can you see this part is red? I cannot highlight either. Well, anyway, I just explain. So so because when I estimate this expectation of epsilon j, epsilon k, when j is k, I will have an additional sigma squared, and that sigma squared is not what I want. So here, when you do the kernel approximation, you need to explicitly extract out the situation when this pair j prime is the same as k prime. So you do not want these two, because you do not want these two, the yj tjj prime and yk tkk prime. You do not want them to be identical. If they are identical, they contributed a term that you do not want. So that's why it's something you have to be quite careful. At the beginning, we didn't do that, and then the result actually has a big problem. So excluding these points, the identical points, and then you will automatically exclude this sigma epsilon square from your analysis, and the result will give you directly this CST estimation. So here, in the end, this is the estimation. We just plug in this approximate version of this E of Yj, Yk using this V hat Jk. Okay, so that's our estimation of the variance covariance function. And then we also have some uniform convergence results. I'm surprised. Why do I talk about this before? Okay. The 2 pages looks like out of order. Okay, so I just presented in theorem 1 the pointwise convergence result. We actually can further get the uniform convergence result. So the uniform convergence result is h squared log n to the power 6. So this is contributed from the bias, and here this is the most important term, that is the delta n with the square root of delta n, and delta n is log n to a certain power divided by n. So this whole thing is actually slower than root n. So uniform convergence rate slower than pointwise convergence rate. That's sensible. That's always the case. And this result also agrees with the non-network situation. So with the non-network situation, you would plug in kW equals to minus infinity. And in that case, you would have this thing is log n to the power 13. And that is agreeing with existing literature. And finally, this convergence rate, because the kW appears there, so it is dependent on this network feature kW. So kW, remember I mentioned this is describing the it's limiting the superstar effect. So kW, if you allow kW to be larger, your network can tolerate more superstar effect. So it has more degree of heterogeneity. So this is saying that the convergence rate is linked to the heterogeneity of your network. The more heterogeneous your network is, the slower the convergence rate will be. The uniform convergence rate will be. Okay, and I think that's. Now I understand why I put that C estimation, the variance covariance function estimation before theorem 2, because I want to present this theorem here. So for the variance covariance function, the estimation, the uniform convergence rate is the same as the theta. So it's also the same expression. So and the explanation is also the same. Okay, so So I just want to say some comments about the proof. Theorem 1 is actually not very hard to prove, but theorem 2 and 3 are actually quite challenging to prove, because we have this network effect. And at the beginning, I felt like, oh, network effect is just an S. But in the end, the network dependence is everywhere. So when you do this proof, this network effect, it propagates to every single aspect of the proof. So nowhere you would have independence. So this, in addition, we are dealing with functional data. So we also have time correlation. So these two things combined together it turns out to be very, very challenging. So we had to use a lot of heavy-duty tools, like the empirical process treatment, non-parametric analysis, and we even, not only we have to use various concentration inequalities on the martingale sequence, we also have to develop some inequalities. For example, the Bernstein's inequality, it's not exactly Bernstein's inequality, but the Bernstein's type inequality under the network structure is not actually available. So we found that we have to establish that inequality first before we can proceed. So that inequality might be of interest itself. Okay, so that's the theory. So now Okay. So maybe let me go quickly. So once you get the matrix, the variance covariance function, the convergence rate, then its eigenvalue, its eigenfunction, they all have the similar kind of convergence rate. So I'm going to maybe I just skip that. And we have only Let me, maybe I just go directly to the, yeah, maybe I just go directly to the data analysis. So this is a quite interesting data set. So this is the, it's a Chinese social network called Weibo. So it's a little bit like the Chinese version of Twitter. So this is the data we are analyzing. We have 1 week data from January 2nd to January 9th of 2014. And the data size we have is 850 active users. And the week started on a Thursday and finished on a Wednesday. So this is the framework we have. And we use YIT to describe the activeness of the user. And so you have some observations. And this YI at TIK, that means at the time TIK, how many posts this person has posted. And the covariates we included are 2. One is the gender, X1, and the other is the number of self-created labels. Some people call themselves a tennis player or I don't know, a tech guru or something like that. So this is their self-created labels, and that's the number of those labels that they create. And to construct a network, we just use whether or not a person I follows a person J. So if I follows J, we use Aij equals to 1. Otherwise, we use Aij equal to 0. So in the end, the density of the network, so if you count all the links between all the possible links you could have, the ratio is 0.47. So this is a very sparse network. So not everybody is connected with everybody. So this is how this Weibo social the data look like. So the time is we put it in the red box. So this is an example of 3 users. So it's the posting time for user 1, 2, 3, and user 2 and 3 are following user 1. So this is just how a snapshot of the data. And here is also an illustration of the data. You have all these 800-something people, and some people posted very little, some people post more. And here, majority seems to be posting between 100 to 160, 80 maybe posts during this period. And the second plot, what you see is for the number of posts by time. So we have 0 to about 200, 160 maybe hours, and this is the number of posts. And you can see that clearly it is up and down, and this is because people don't post at night. They post during the day, so that's why you see the numbers going up and down. And so here is the result of the estimated. Here you have rho hat of t. This is the beta 0 hat of t, beta 1 hat of t, and beta 2 hat of t. So rho hat of t, you can see, first of all, in all those analysis, you can see clearly there's a daily activity that is reflected here. You have, every day you have up and down. So that's the first feature. And then the second feature is that you can see that during the weekend, so we started on a Thursday, so Thursday, Friday, and then weekend. So during the weekend, the friends effect, the rho t seems to be bigger. And during the weekdays, maybe you are more influenced by other things. So the followers effect is smaller. So this seems to be the situation. And intercept, I cannot say much, but this beta 1t and beta 2t, you can see that also in certain days, 1, 2, so this is a Sunday, Thursday, Friday, Saturday. So between Saturday and Sunday to Monday, this is lower, and all the other days it's higher. And this is the coefficient in front of gender. So according to our labeling, this means that male users, they are less active on weekend, and they are more active on weekdays, less active than the female on weekends. And then finally, this is the coefficient in front of the number of self-generated labels. So you can also see that on weekend, it's lower, it's negative, and on other days, it's more positive. So that means the more you generate your self-labeling, you are less active on weekend. So it could be that, when you have a lot of self-labeling, you are active, you have an active lifestyle. So maybe on weekend you have other things to do than posting. Okay, so yeah, so this is just what I mentioned. And so here is the functional principal component analysis result. We find, I didn't mention how do you choose the number of components. We use a certain BIC criteria and actually use without using the composite likelihood, use the classic likelihood as a criterion to do the BIC. And this has chosen k equals to 3. And these are the three principal components. And you can see that, first of all, they also have the daily activity kind of pattern. And the first component is reflecting just the general periodic. And the second one seems to be more reflecting the weekday activity. And the third one is more reflecting the weekend activity, because the two peaks are in the middle of those 2 days. Okay, so, and we also did a comparison between without using the functional structure and using the functional structure. And the IMSE turns out to be quite different. So that means the functional data nature is actually present here in this data set. And okay, so let me just finish up. We handled functional covariates. We didn't, but we could handle functional covariates, XIT, and this turns out to be actually straightforward. So this is to be done and it can be readily done. And we could also incorporate varying coefficient network. So our W right now is fixed, but if it's a friendship relation is changing a long time, if it's WT, you can also handle it. It's more complex to handle, but it's also doable. So this is also something readily doable. Now, two things that are harder to do. One is the high-dimensional covariate situation. So if you have high-dimensional covariate situation, you always have a lot more complexity. So that's something that has not been done. And the fourth one is a little bit related to the first question that we have. So we have incorporated the dependence of the current friends, of the friends of the current action of the friends. So if you want to incorporate the serial dependence of the past action of your friends, then how do you do? So this is one possibility that we can think of. Right now, this relation is the description is here, and if you want to incorporate the past action of your friends, you could replace this yjt with yj tau, and you can integrate out this tau from 0 to t. But this probably will cause a lot more complexity. So it's something that is very interesting and it's worth looking into. Okay, so I don't know why it takes too long. So thank you for your attention.
Thank you. Thank you, Yan very much for this wonderful talk. Either the audience here or the Zoomers, you can feel free to ask a question. We have a few minutes to handle the questions. For the Zoomers, you should be able to unmute. But in any case, you can either, you can either unmute yourself or just type on the chat. Okay, no more questions?
typing is always annoying.
Yeah. Okay, if no further questions, and thanks very much for your attention, everyone, and thanks Yan Yuan again.